Hello everyone, welcome to the Piano Lessons 123 web series. I am making this series to help anyone who wants to begin learning music theory and doesn't quite know how to start. This series will start from the very beginning and move upwards and upwards until you have pretty much everything you need for college music theory. I would normally start this series with something like notes and staves and clefs and things like that. However, I wanted to step back one unit and go to the nature of sound. This is going to be more of a science video, and you might only watch this if you have a particular interest in sound. I think it's great information to know. It's helped me, and if you're interested, keep watching. If you're not interested in the science behind how sound works and how sound travels, then fast forward to the next video and we can begin with clefs and staves and notes. So first off, we need to think about what is sound. Well, standing outside, or inside for that matter, you're standing in air. And air is a mixture of what? Molecules. Hopefully there's some oxygen there. And these molecules are moving around all a bit. They're moving at a certain speed, a certain range of speeds, determined by the temperature. But if there's no draft and there's no fans, the air is still. And sound, it causes movement of those air molecules. Not a movement you really feel like a ceiling fan or like a breeze, but a more rapid movement. And how does this happen? Well, we're going to talk about that. So sound is really a type of pressure. And that pressure is created because when you have two molecules that are moving around at a constant rate and bumping into each other, and that's a pretty normal thing to happen, if you start changing that, well, then you create sound. And you have to create it at a pretty rapid rate. If you think about sounds that we can hear, let's say 10 million hertz, that sounds like a big number, and that means 10 million oscillations per second. So you are causing a pressure change in the air, and that pressure change is happening 10 million times a second. We'll get more into that in just a second. So what is sound? Sound is a wave, and you might think of waves like those in water. And we're going to start off with transverse waves. And transverse waves are not what sound is. Sound is a longitudinal wave, and we'll describe the difference between those in just a bit. But let's start off with a transverse wave. I hope that if you're watching this and you're curious about the science behind sound, you have some basis in science and something to build off of. I'm not starting from zero, but I am starting somewhat at the beginning. So if you think about sound, I'm going to plot a wave, and I'm going to start with a vertical axis and a horizontal axis. Now, imagine that this is a body of water, and this is sort of the bank or the edge. Well, there's no movement on the water, right? It's still, there's no wind, there's no boats, there's nothing. There's no energy, nothing's really moving. Well, if you drive a boat by or the wind picks up, you might observe something like this, where you have these swells and these dips and these swells and these dips. And then after some time, the water will return to its zero state. That's not how a wave is exactly, but it's a good place to build from. So what does this mean? This seems kind of strange still, sort of abstract. Well, this, as I mentioned before, is something that we call a transverse wave. Transverse. And what does that mean? Well, the first thing to know is that waves carry energy. And by carrying energy, they can do work. For example, you hear a loud sound. That loud sound might cause some ear pain. That's because it is actually causing the organs of your inner ear to move a little bit more than they should. And that is doing work. Or let's think of solar power. Light shines and it causes charge to build up. We can save that charge in a battery to be used later. Well, that requires work. So let's think of this wave moving. It is moving from this starting point, and it is moving to the right. and we have a consistent propagation of this up and down action. We have these crests, these high points, and these troughs, and these low points. Now, imagine that you're looking out on a body of water, and the waves are moving towards shore. So here you would be over here looking out into the water, and it seems like the waves go on forever. And imagine you see a buoy floating on one of these peaks, on one of these crests or waves. Well, that buoy is going to move up, and it's going to move down, and it's going to move up, and it's going to move down, and it's going to swell with each of these waves. So a transverse wave carries its energy perpendicular to the direction of the wave. So the wave, we said, was moving from left to right. And so if you imagine this buoy stays in the same place all the time, well, at this time, there is a crest here, a high point. At another time, it will approach the 0 mark, and then later on, it will go back down to the low point, and then it will rise up to the middle point, back up, and it will continue on this path over and over until, well, I suppose if you're on the water, until the winds die down or the boats stop going by. But in sound, this would continue until that pitch that's being sounded from a source, whether it's a person or a speaker or an instrument, stops. So the energy is moving perpendicular. The wave is moving in this direction. And what does this mean? Well, imagine that there's some stormy weather. And at the time of this video, Hurricane Dorian is moving along the coast. So there's some stormy weather in the US. And the water begins to swell more than usual, right? So this buoy is going to move a lot higher than it did before and a lot lower than it did before. Now, this is the 0 point. If we're at the 0 point, we have no energy at that point in time. And just because this is a low point doesn't mean that we're taking up energy or that we don't have energy. In fact, this point has the same amount of energy as this point. They're just opposite direction. It's like you can go 5 miles per hour north or 5 miles per hour south. You're still going at the same velocity. You're just going in a different direction. So these swells, or this crest and this trough, would be deeper or further from the 0 point. So really, what this axis measures is amplitude. Now, amplitude you might think of as volume of sound. When we have a speaker that's set to a really high volume, we move lots of air at one time. If you've ever been to a concert, you know that the speakers they have are probably bigger than something you have in their house, because they have a large venue to provide the sound for. They must move a lot of air. If you're very close to those speakers, it might not be the most enjoyable concert. It might be a little too loud for you if you don't have earplugs. So they are moving lots of air. The amplitude is great. Now, you probably know this already, but if you stand really far away from a sound source, you're probably going to hear a quieter sound than if you stood very close to that sound source. So, in reality, this wave starts to diminish as you move further from the source, and eventually you'd get far enough away that there wouldn't be a wave anymore, right? And in theory, the bigger amplitude that you start with, the further away you could go before it decays all the way. The wave is gone. So we already mentioned that this is a transverse wave, and this is how light is. Electromagnetic radiation, ultraviolet, visible light, infrared radiation that we feel as heat. Those are all transverse waves. Something that's a longitudinal wave like sound has the same principle, but is a different type of wave. So let's think of a speaker. I'll draw one here for us. You're listening to your favorite music on this nice little 1970s speaker, and it's producing sound. And you think of the sound waves kind of like the gills of a fish. I'm sure you've seen sound illustrated this way before, and the sound propagates outwards. Now, from this drawing, it looks like the sound is only going to the right, but in reality, you have to imagine this as this sphere of sound that radiates outwards, right? It goes in every direction from the sound source. It goes behind, in front of, to the left, to the right, above, and below. And as you get further from the source, the volume will be less, the amplitude of the wave will be less. Well, the way sound works is you have something moving air, and that causes dense areas of air. So we have something that looks like this, and then you have something that's more sparsely populated, and then something that's more dense again, and then something that's more sparsely populated. And we have certain names for these areas of air. And again, let's consider this wave is moving this way, left to right. What we call this dense area of air is called a compression. We have lots of molecules in this area, and what we call this more sparsely populated air is a rarefaction. Now we're going to compare these two because in fact you can represent a sound wave with this diagram, but a transverse wave actually looks something like this. A sound wave looks nothing like this. It looks like this instead. But of course not in a line, in a sphere radiating out from your source. So in this direction, and this direction, and this direction, and this direction, and this direction, every direction around the source. So first of all, we need to think of something. How often do these oscillations happen? How often do we get a crest and then a peak, or a crest and then a trough, crest, trough, crest, trough? How often is that happening? Well, we describe that as frequency, or how many oscillations per second. And in general, the higher the frequency, or the higher this happens every second, the higher the pitch you will hear. So for low pitches, or those low rumbly notes that everyone loves, this is happening less than for the high frequencies. So how do we measure that? Well, you have to pick 2 points on that line that are the same. And what do I mean by that? If you want to start from a 0 point, you have to include a crest and a trough, and then the 0 point. So what I'm saying is, you can imagine that here's one unit, and then from here to here is another unit of the exact same thing. So here's one thing, and then here's its identical twin, the repeat. You could also do that from peak to peak, or trough to trough. It doesn't matter where you start as long as you get all the way back to the same point. Imagine a grandfather clock. The pendulum is at the center. First it swings left and comes back and passes the center, then it swings to the right, and then it comes back to center. So left, right, center. That's one oscillation. How long did that take? You could time it. Well, if you think that it's 1 second and 1 second and back, your clock is probably in time. It might vary from that, but it's probably somewhere around 2 seconds per full swing. And how does this help us? Well, we can measure this, and this number of cycles per second is measured in something called frequency. Frequency. Do you go out to dinner often? Yes, we go out pretty frequently. It happens often. Frequency. And that is measured a certain way. It's usually measured by something of cycles per second. Or you might see 1 over seconds, which is in fact equal to something you've probably heard before, hertz. The unit of hertz means cycles per second. So in other words, if I'm listening to a pitch that is occurring at 10 million hertz, that means that I'm having this series of crests and troughs 10 million times every second. So that means that they're pretty small, right? They couldn't happen if they took up a large amount of space. Well, now that we know frequency a bit, we should talk about how we can overlay a longitudinal wave with a diagram that looks a lot like a transverse wave. And it's kind of difficult to do, which is why we started with a transverse wave. But let's think of it this way. I'm going to draw a single point on this line. Now that point is not going to move, but instead think of that point as a listener to a sound. Or in other words, the sound wave is moving by that single point. So at this current position, the point is located with respect to a sound wave in a dense or a sparsely packed area, or a rarefaction. And now, if you think about it, compression, right? When you compress something, let's think about you're packing your suitcase and you want a little bit too many of your clothes to go with you. You have to smoosh them down into the suitcase for them to fit. It takes energy, right? If you were just to throw a few things in an entirely empty box, well, that would be pretty easy, and then you can close the zipper no problem. So this rarefaction that is sparsely populated with respect to a compression, well, that's an area of low energy. So I would presume that, as we said before, the 0 point is low energy, right? Well, now imagine that the sound wave is moving to the left. So you're waiting, and now eventually compression is coming near, right? And so the energy of that at that point, at that single point we marked, is moving towards its high point, right? And now that compression is starting to pass, and we're getting back down to a rarefaction. Right at the center of the rarefaction, our energy will be 0, or near 0. And now a compression is approaching, and we approach the center of the compression. The compression is leaving. Eventually we approach a rarefaction, and we're at the center of a rarefaction. So imagine this moving by. Low energy, high energy. So at this point, we keep getting oscillations of high energy, low energy, high energy, low energy, high energy. And the direction of these isn't really important. It's just important that you understand that these things that are far away from 0 are points of high energy. So this kind of wave that we're talking about, sound, is a longitudinal wave. And what that means, the transverse wave, we said we imagine a buoy on a swell in the water. It would move up and down. So the work being done is taking the buoy up and down, even though the wave is moving this way. So the energy is perpendicular to the wave, the direction of the wave. In longitudinal waves, the energy transfer is parallel to the wave. So if the wave is moving left to right, so is the energy. So imagine that a super loud sound was produced, and that would be moving a ton of air. You might actually feel the wind from that energy pushing on your face or pushing you back. It might feel like wind even. And that wind would be pushing on your face against you, probably opposite direction of the source of that sound. Whereas light or transverse waves move objects, if they were going to move an object, perpendicular to the wave. So now we have the basis of sound. Sound is a wave. It can occur at different frequencies, and the frequency is what we perceive as pitch. So pitch is a perception. Just like color doesn't really exist, color is a perception. Instead, there are different frequencies of visible light, and our brain assigns them a color so that we can perhaps describe them or remember certain things. Sound is the same thing. Pitches and timbres, timbres being the tone of that pitch, they're more of a perception, whereas the real thing is a frequency of a longitudinal wave. This seems kind of abstract. Let's bring it a little bit closer to music. So let's think of a piano, and let's think of a piano in a big auditorium. So you're lucky you get first row seating, you're right near the piano. Well, what if you're not so lucky and you sit really far away from the piano? Well, in all actuality, if you're that far away, you might hear the sound at a different time than the person sitting right next to the piano, or maybe even the pianist. Sound has a speed, just like pretty much anything moving does. And the speed of sound is this. It is 340 meters per second. So in every second of time, sound has gone 340 meters. That seems insane to me. It's hard to imagine. That seems fast, right? Well, by comparison, the speed of light is 300 million meters per second. Sound and light. So there's almost no comparison. Now what does this mean? This means something that you've probably already noticed, that if you're really far away from something that produces a sound, you might hear a delay between when that sound was made and when you heard that sound, whereas the person right near the sound source probably heard it right away, or so close to right away that they didn't even notice a delay. Well, let's take it a step further. Let's move on to something else. Let's move on to frequency of a pitch on a piano. Well, if you've ever looked inside of a piano, you'll notice that there's all of these piano strings, which are actually made of metals, so they're more like wire. And if you've ever taken the time to look at the bass section, they are usually very thick strings and they're very long. If you look at the treble section, they're usually thin and short. And there is a reason for this. The construction is actually based on this principle, which is a physics equation, and forgive me for showing you this, but I think it's a useful bit of information. I'll describe this. So we have F equals 1 over 2L times the square root of T over Greek letter mu. What does this mean? Well, F is frequency. We know that frequency means the number of oscillations per second. We don't know the other letters yet. So L refers to the length of the string, T refers to the tension of a string, and mu refers to the density of that string, or, in more simple terms, the thickness or the diameter of that string. So let's work out this equation a little bit. Frequency equals 1 over 2L. So let's word that as frequency is inversely proportional to 2 times the length. So that means that longer strings want to resonate at a lower frequency, right? 1 divided by a big number is smaller than 1 divided by a very small number. So if we increase the length of the string, that string wants to vibrate at a low frequency. And that's convenient to do because if we make a piano string long, then it wants to vibrate at a low frequency and we can produce that frequency pretty easily. If we make a string long, we could still possibly get that frequency, although not as easily, by manipulating the other parts of this equation, tension and thickness. So frequency is proportional to the square of the tension. So or the square root of the tension, as you increase the tension or you hold the string tighter on each end, the frequency will increase. You might have had this experience pulling on an elastic band and then strumming it, or pulling on a string and strumming it. You can actually get a frequency from it. Perhaps you've heard the guitar. The guitar works on that principle, as does the violin, the piano, cello, pretty much any string instrument you think of applies tension to a string to get a frequency. Greek letter mu, or density. So, as we said earlier, the bass strings of a piano are very, very thick, and this increased thickness makes that string want to vibrate at a lower frequency. And as we mentioned, that you can still get low frequencies from strings that are not very long or not as thick as they should be by applying less tension. That tone will not be as pleasant, as pure, as powerful. So things have resonant frequencies. You might have experienced this driving in a car, a poorly maintained car. You drive in the car, you hit a certain speed, and all of a sudden the steering wheel starts to shake or starts to vibrate, or you hear a certain whirring sound, and you get nervous, but you don't quite have the money to fix the car, so you don't. But you live with the sound. Well, you've hit the resonant frequency of whatever thing is broken, and now you can feel it. Because when you hit a resonant frequency, that frequency tends to be very strong and pure and powerful. Whereas if you try to get a frequency from something that's not at its resonant frequency, it is less of those things. So when your piano goes out of tune, you call the tuner, they come in, and they go through the piano, and if the piano is flat, meaning the pitch is lower than it should be, as opposed to sharp, where the pitch would be higher than it should be, they will put the tuning hammer on the tuning pin, and they will crank it so that the piano string is held tighter in the piano, or you are increasing the tension on that string So you will raise the frequency until you hit the right pitch. If the piano is sharp for some reason, they will relieve some of the tension, which will lower the frequency. The length and, of course, the thickness of the strings is sort of already set by whoever engineered and built the piano. So how does all of this translate? We have sound. We know it's a wave. We know it travels very fast, not that fast compared to light. And we know that materials, such as strings in a piano or on a string instrument, have a certain frequency that they like to vibrate at, and that's how we produce the sounds we want. Well, how do we perceive this? How do we sense and then perceive this? Well, we sense this through our ears, and we'll get into some of the specifics. The sound that you hear is a frequency of pressure change in the air. The air keeps colliding into each other and moving along in that longitudinal wave we drew out earlier, and that presses on your eardrum, or it bangs on your eardrum, or your tympanic membrane. This eardrum transmits that energy to three little bones called ossicles. The ossicles work to amplify that sound so that your sensory organs can actually sense things better. Those organs are called the hammer, anvil, and stirrup, or malleus, incus, and stapes. So these amplifying organs help you sense the sounds or pressure changes better. These organs then act on an organ known as the cochlea. We'll draw that out. That word might look familiar. You might know that there is such a thing as a cochlear implant, which sort of acts to bypass the ossicles and work on your cochlea in a more exaggerated fashion to help people who were born deaf to hear. And it's not quite the same hearing as you probably have listening to this video, but it's an improvement, often. So the cochlea is a snail shell shaped organ, very small, in your inner ear, and it's filled with fluid. Well, those three little ossicles pound on a part of the cochlea that causes the fluid inside to vibrate. This fluid is called perilymph, and this fluid movement is what causes little hairs on an organ called the organ of Corti. So imagine these hairs sitting in still fluid when there's no sound. A sound comes along and vibrations through the fluid causes these hairs to wiggle back and forth. And it is this movement of these hairs that sends an action potential or a signal to your brain, which is then perceived as sound or a pitch for a certain frequency. And the interesting thing is the cochlea has this winding to it, as we said, the snail shell shape, and as you go along it, in different areas, the hairs will resonate at different frequencies, and that's how we can distinguish one pitch from another, because there is localization of where these frequencies will be received. So now we have some basis of how we hear, and we understand that pitch and sound and music is all a perception of something that is really just different frequencies of pressurized air moving around us. And the interesting thing is we can hear different pitches in different instruments. We can hear a voice, we can hear a piano, we can hear a violin, we can hear a tuba, and we hear all of these things at maybe the same pitch, but we know that they're different things because they have a different timbre or sound quality. And the thing about all of these different sound sources and their timbres is that they aren't really pure pitches. Instead of having a single frequency ringing out, they have some amalgamation of many different frequencies, and the net is the pitch we hear. However, it's those little differences between them that give them their unique sound. And the next thing that goes further is, how do we apply this to music? Well, we've talked about all this science, and you might be thinking, well, science isn't really music, and I would have to argue with you. I won't, but I could. And when we look at this first movement of Beethoven's Moonlight Sonata, Adagio Sostenuto, you see a bunch of notes on paper. More specifically, you see these little black dots that represent different pitches on 5 lines and 4 spaces, called a staff, and that tells us which pitch to play. And not only does it tell us which pitch to play, it tells us which pitch to play, in which order, at what point in time. So really, music is sort of a science. It's a documentation of pitch versus time. You can imagine it as a graph, where on the y-axis we have pitch, whereas you go down the page and in through treble clef and into bass clef, you have lower pitch or lower frequency. As you go higher on the page or up through treble clef, you have higher pitch or higher frequency. And as you move to the right, you move further in time. So here's the beginning of the piece, and as we go through on and on and on, we get to the end of the piece. So you would know that this pitch is higher than this pitch, and you know that this pitch comes after all of these pitches and before all of these ones. And in the next video, we are going to get into how to read the letters of these pitches and apply them to the piano. And we are going to get into the technical aspect of piano and the basics of music theory. I hope you enjoyed this video. I hope to see you in the next one.